Cambridge, Massachusetts, 1937. The air around Harvard Yard carried the quiet rhythm of academia, footsteps on old stone paths, the echo of bells, and the murmurs of students drifting between classrooms. But inside a narrow laboratory, tucked behind the walls of the Graduate School of Engineering, one man worked with an intensity that felt out of place in this peaceful setting. Surrounded by wires, relay switches, gears, and stacks of mathematical tables, Howard Hathaway Aiken was fighting a war that hadn't begun yet. He wasn't a soldier. He wasn't even interested in strategy or geopolitics. Aiken was obsessed with a problem most people didn't even see: human error. Every calculation required for navigation, artillery, ballistics, naval gunnery, every trajectory, every table, every number, depended on teams of mathematicians working by hand. A single mistake could redirect a shell, mislead a bridge crew, or alter the fate of a mission. Aiken had spent years watching students and fellow engineers fight their way through endless equations, drowning in logarithms and trigonometric functions. He saw fatigue, frustration, and mistakes repeating over and over. For him, the question was simple: why trust humans with tasks a machine could do better? Aiken was already known on campus as the kind of engineer who refused to believe in limitations. Born in Indiana and raised in an era when mechanical devices powered industry, he grew up fascinated by machines that could amplify human ability. But at Harvard, he found a different kind of inspiration: mathematics so complex and repetitive that they practically begged for automation. He believed the world needed a device that could think numerically, operate tirelessly, and deliver answers with perfect consistency. His professors dismissed the idea as unrealistic. Harvard was a place of tradition, scholarship, and theory, not industrial machines that rattled, buzzed, and clicked. But Aiken didn't care about tradition. He cared about efficiency. He studied old works by Charles Babbage, the 19th century dreamer who designed a mechanical computer long before electronics existed. Aiken recognized something no one else had fully appreciated. Babbage wasn't a relic of the past. He was a blueprint for the future. With this realization, Aiken began drafting plans for a machine that could finally bring Babbage's vision to life using modern engineering. But the scope of the idea was overwhelming. It would require thousands of components, miles of wiring, and a budget far beyond anything Harvard could offer. Aiken had a mind capable of building it, but not the resources. Then came the turning point. Aiken approached IBM with his proposal, a bold request for a machine the world had never seen. Instead of skepticism, he found an unexpected ally in Thomas J. Watson, IBM's president. Watson wasn't just a businessman. He understood the power of ambition. He agreed to give Aiken what he needed: parts, engineers, funding, and a team capable of turning theory into reality. In that moment, Aiken's dream shifted from an academic fantasy into a national project. Construction began quietly. There were no headlines, no military officials, no journalists aware of what was forming in the shadows of Harvard's laboratories. The machine, at this stage an unnamed giant, grew piece by piece. Steel frames, rotating shafts, magnetic relays, porcelain insulators, and gear-driven counters began to fill the lab. What emerged looked less like a mathematical tool and more like a mechanical organism. Aiken pushed relentlessly. He wanted a machine that could compute continuously, handle complex sequences, and operate with precision no human could match. It wouldn't simply perform calculations, it would execute logic. The machine consumed years of work. It stretched more than 15 meters long and weighed nearly 5 tons. It used 750,000 components, thousands of switches, and miles of circuits. It was as loud as a factory line and as meticulous as a watchmaker's creation. It was unlike anything America had built before. As the world outside spiraled toward conflict, Germany rearming, Japan expanding, Europe destabilizing, Aiken's machine moved closer to completion. And although he didn't know it yet, the timing was perfect. War was coming. When it arrived, armies would need calculations faster than any mathematician could produce. Artillery tables, torpedo trajectories, bombing coordinates, naval models, everything depended on accuracy and speed. Aiken's invention would become indispensable. By 1943, the machine officially received a name, the Harvard Mark I. It was the first large-scale automatic computer in American history. It wasn't electronic yet, that era would come later, but it could operate continuously, compute complex equations without fatigue, and produce results with consistency that humans could never match. Engineers watched in awe as it solved in minutes what once required days. And as whispers of the war's growing demands reached Harvard, the US Navy took notice. They didn't understand the full capabilities of Aiken's machine, but they recognized one thing clearly. Precision would decide battles, and Aiken had built a factory for precision. From this moment on, the Mark I would no longer belong to academia. It would become a weapon, silent, tireless, and essential. And as his creation prepared to enter the war, Aiken understood that this was only the beginning. His vision had expanded far beyond eliminating human error. He now stood on the edge of a technological revolution. If you want more stories of forgotten engineers who shaped history in ways the world never noticed, consider subscribing so you don't miss the next chapter, because Howard Aiken's greatest impact had yet to begin. Could one machine really change the course of a global war? And was the world ready for what came after? When the Harvard Mark I finally took shape in 1943, it didn't look like an invention meant for a university. It looked like a machine built for a new era. A wall of metal, relays, rotating shafts, clacking counters, and blinking indicators stretching across an entire room. But long before it reached this final form, the machine existed only as a bold vision inside Howard Aiken's mind. What emerged over years of work was not just a device. It was the first American step toward computers as we know them. The journey began the moment Aiken realized Harvard could no longer contain the project. No laboratory on campus had the industrial capacity to build something on this scale. That's why his partnership with IBM became essential. IBM's engineers were used to tabulating machines, punch card systems, and precision electromechanics. But Aiken's proposal went far beyond anything they had attempted. He wanted automation, memory, conditional logic. The foundations of computation. IBM saw an opportunity to leap into the future, and Aiken saw the only path forward. The construction moved to IBM's Endicott plant, where a team of engineers, machinists, and technicians worked on components that had no precedent. Aiken visited frequently, pushing the team to test every relay, every gear, every sequence. He had no patience for delay, and even less for inefficiency. The machine had to operate flawlessly. After all, its purpose was to eliminate human error. It could not introduce errors of its own. Piece by piece, the Mark I grew. Steel frames formed its skeleton. Miles of wiring gave it nervous pathways. Rotating shafts synchronized its movements with mechanical elegance. Electromagnetic relays served as its logic cells. Primitive, slow by modern standards, but revolutionary for the time. Punch card readers provided data. Mechanical counters displayed results with stunning precision. When assembled, the machine felt alive. Its switches clicked in rhythmic patterns. Its gears murmured in steady rotation. Its lights pulsed gently as calculations moved through its circuits. Operators said it sounded like a mixture of a factory, a clock tower, and an orchestra warming up. But what mattered most wasn't its appearance or its noise. It was its capability. The Mark I could solve a problem without stopping. It could read instructions automatically, follow conditional steps, and execute calculations for hours without fatigue. It took sequences humans dreaded, long chains of polynomial equations, differential calculations, or ballistic trajectories, and processed them with mechanical discipline. Every rotation of its shafts moved information. Every click of its relays pushed logic forward. It wasn't fast compared to future machines, but it was relentless. That relentlessness was what the war demanded. When IBM delivered the completed machine to Harvard in February 1944, it was so massive that workers had to remove windows to bring it inside. The Mark III was installed in the Cruft Laboratory, a building that suddenly looked too small for the future it now contained. The room transformed into a buzzing heart of computation. Students and researchers gathered to watch the machine process instructions encoded into punch cards. Long strips of numbers, commands, and loops that the machine consumed with unwavering precision. Aiken wasted no time introducing his strict philosophy. He ran his laboratory like a naval command center. White gloves were required. Silence was mandatory. Every operator followed procedures with military discipline. Aiken believed that if human error had no place inside the machine, it should have no place around it either. Many students found Aiken difficult, even intimidating. His expectations were impossible for some, inspiring for others. But the atmosphere he created allowed the machine to perform flawlessly. Under his leadership, the Mark I became not just an engineering marvel, but a symbol of a new scientific culture, one where precision, rigor, and automation would define the future. As the machine stabilized in its new home, Aiken began exploring what it could do beyond basic computation. He tested logical branching, iterative loops, and multi-step sequences. He pushed its mechanical mind to the limit, exploring what happened when instructions were layered, chained, or repeated. He discovered that with careful programming, the Mark I could solve not just calculations, but problems. And that was when the US Navy intervened. War had intensified. Submarines prowled the Atlantic. Artillery crews depended on accuracy. Bombardiers needed reliable trajectories. Commanders needed computations faster than human teams could produce. The Navy realized that the Mark I wasn't a research curiosity. It was the answer to a growing strategic crisis. Officers visited Harvard and watched the machine compute tables essential for naval warfare. They saw it perform days of mathematical work in mere hours. They understood immediately that Aiken had built something the military had never possessed, a device that could give the United States a computational advantage no other nation could match. The Navy formally commissioned the Mark I for wartime service. The machine that began as a dream in Aiken's mind was now a confidential weapon, not a gun or a plane, but a machine that supplied the numbers behind every shot fired, every torpedo launched, every trajectory calculated. The partnership between Harvard and the Navy changed the laboratory's atmosphere. Uniformed officers walked the hallways. Security tightened. Calculations for classified missions became routine. The machine ran day and night, its gears never resting, its relays clicking in steady sequences. Harvard had become an extension of wartime industry. Aiken supervised every step, every program, every instruction set. He knew the machine's value. He knew its power. And he knew the war needed more than mathematical accuracy. It needed reliability. In that moment, the Mark I stopped being an experiment. It became a battlefield asset. And as the demands of war intensified, the machine Aiken built would face its greatest test. It would be pushed to its limits, relied upon by officers who had never heard of Charles Stark Draper or Howard Aiken, and used to shape decisions that changed the course of the conflict. As Aiken watched his machine enter the war, he couldn't help but wonder, had he built a tool to help humanity, or a device that would push war into a new era of technology and dependency? By the summer of 1944, the Harvard Mark I had fully transformed from an academic experiment into a strategic asset. Its long frame hummed day and night, gears turning in steady cycles, relays snapping in precise rhythm. What began as Howard Aiken's attempt to eliminate human error had become a silent weapon, one the US Navy relied on more than any aircraft or ship captain would ever know. War had reached a stage where battles were no longer won solely through firepower. They were won through information, through calculations, trajectories, distances, angles, and models so complex that human teams couldn't keep up. Every error cost lives, every delay risked defeat. Precision was no longer an advantage, it was survival. And the only machine capable of delivering that precision at the speed the war demanded was the Mark I. The Navy assigned a group of officers to operate the machine, turning the laboratory into a hybrid between a university research centre and a military command post. Uniformed men stood beside engineers in white gloves, feeding punch cards into the machine in long sequences. They brought in requests directly from naval bases, fleet commanders, and weapons specialists. The Mark I processed them relentlessly. One of its most critical tasks involved generating artillery and ballistic tables, the mathematical guides that allowed gunners to hit targets across vast distances. Before machines like the Mark I, these tables required entire teams of human computers working for weeks. Now, the machine could produce them in hours. No fatigue, no inconsistency, no missed digits. Aiken used to say that the Mark I didn't simply speed up calculations, it reshaped how the military planned combat. Another major demand came from the Navy's Bureau of Ordnance, which required precise calculations for torpedo trajectories. Torpedoes were notoriously unreliable during the early war years. Tiny miscalculations caused catastrophic misses. The Mark I helped correct that. It simulated water resistance, angles of attack, firing distances, and mechanical tolerances faster than any manual method. Submarine crews at sea never knew that the accuracy of their weapons depended on a massive machine hidden inside Harvard. The Mark I also supported aerial bombing missions. Long-range bombers needed precise navigation, fuel modelling, and release points. If the numbers were off by even a small margin, bombs could miss by hundreds of meters. The machine computed new trajectories based on weather conditions, wind speed, altitude, and drift. Pilots flying over the Pacific or Europe used tables and data produced by Aiken's creation, though few ever learned its name. Aiken's relationship with Navy officers was often tense. He insisted that every program entering the machine follow strict rules. Sloppy punch cards, poor formatting, or imprecise coding could cause sequences to break. To Aiken, that was unacceptable. The war demanded perfection. The machine demanded discipline. Some officers found him difficult, others respected him for the same reason. But none could deny that his standard was the reason the Mark I performed with such reliability. Inside the lab, a new profession quietly emerged, one that would shape the modern world: programming. Aiken trained teams of students and operators, many of them women, to design punch card sequences, manage logical flows, and correct errors. They weren't just feeding data, they were controlling logic, creating structured instructions, and building early algorithms. Without realizing it, Aiken was establishing the foundations of computer science. But even as the machine proved essential, the work carried enormous pressure. Calculations for classified missions arrived without explanation. Operators never knew whether their work supported a naval engagement, a bombing raid, or a submarine patrol. They only knew the numbers had to be right. The machine became a heartbeat of the war, steady, tireless, and hidden. Aiken continued refining its capabilities. He pushed operators to experiment with conditional loops, sequences that allowed the machine to repeat actions until a solution emerged. He explored hybrid processes, where mechanical counters fed data into new calculations without human intervention. Every improvement expanded what the machine could do. There were flaws, of course. Sometimes relays stuck, sometimes gears misaligned, sometimes punch cards jammed in their guides. But every malfunction was met with rapid correction. Aiken had built a team capable of repairing the machine as quickly as it worked. Downtime was minimal. Reliability became its defining trait. Naval officers reported back to Washington that the machine was indispensable. They praised its accuracy, its speed, and its contribution to combat planning. For the first time in history, the US military had a computational advantage, an engineer's victory, not a general's. Yet Aiken received almost no public recognition. and he preferred it that way. As he once said to a student, the machine's work is more important than the story behind it. By late 1944, the Mark I was running at full capacity. The Pacific campaign intensified. The invasion of Europe was underway. Weapons grew more complex every month. Every new technology required new data that only the Mark I could deliver. The war machine was evolving, and Aiken's invention sat at the centre of that evolution. For many soldiers on the front lines, the outcomes of battles seemed to depend on skill, bravery, and luck. But behind the scenes, the Mark I shaped decisions, corrected errors, and guided strategies. It was the invisible force linking mathematics to survival. If pilots flew safely through storm clouds, if battleships adjusted their guns accurately, if torpedoes struck with precision, the Mark I had played a role in the shadows. And as the war intensified, Aiken began to realize that the machine he had built was not just solving calculations, it was changing the expectations of warfare itself. Human speed was no longer enough. Human vision was no longer enough. Machines would take the lead. If you want to keep exploring the stories of hidden engineers who built the future long before the world understood their impact, consider subscribing, because Howard Aiken's journey is about to enter the most critical chapter. Had he created a tool that enhanced human ability, or a machine that signalled the beginning of a world where humans would no longer keep pace with their own inventions? By early 1945, the Harvard Mark I had become more than a computational machine. It was a quiet force woven into the fabric of American warfare. It produced ballistic tables that shaped artillery strikes from Europe to the Pacific. It refined torpedo models that corrected years of failures. It calculated trajectories for bombing missions, naval navigation, and experimental weapon systems. For the military, the Mark I was no longer an engineering marvel. It was an operational necessity. Yet despite its influence, the machine remained hidden from the public. Soldiers never heard its name. Newspapers never mentioned it. Historians barely noticed it at first. It worked behind layers of secrecy, buried inside Harvard's Cruft laboratory, far from battlefields, but deeply connected to every front. The Mark I didn't fire guns, drop bombs, or steer ships, but the numbers it produced shaped the decisions of everyone who did. As the war approached its peak, demands on the machine grew heavier. The Navy wanted faster tables. Weapons designers wanted new simulations. Ballistic officers needed updated calculations for improved artillery. The Mark I ran almost continuously, its gears clattering through long nights, while operators monitored its rhythm like an engine room crew. For Aiken, each new request confirmed what he'd believed from the start. Precision would define victory, and machines would define precision. But the machine's success created new pressure. The Mark I was powerful, but it wasn't alone anymore. Laboratories across the country were experimenting with electronics, vacuum tubes, and faster logic circuitry. While the Mark I used electromechanics, relays, and gears, other institutions were shifting toward fully electronic computers. These new machines promised speed that the Mark I could never match. Aiken's creation was revolutionary, but it was also becoming a bridge to something far more advanced. Still, during the final stages of World War II, the Mark I remained irreplaceable. Its reliability mattered more than speed. Relays rarely failed. Mechanical parts could be repaired quickly. Operators trusted its outputs implicitly. It delivered results day after day, while electronic experiments still flickered and stalled under heavy loads. Wartime didn't reward potential, it rewarded certainty. And the Mark I's delivered certainty better than any other computational device available. One of its most significant contributions came during the final Pacific campaigns. As American forces closed in on Japanese defences, naval gunnery required flawless modelling. The Mark I calculated long-range firing solutions for battleships engaged in multi-hour bombardments. It simulated the effect of wind, humidity, barrel wear, and ship movement. Its tables guided operations that involved thousands of shells fired across miles of open water. The machine also supported aerial operations during the strategic bombing of Japan. Navigation tables. For B-29 Superfortress crews depended on precise, updated data. Without accurate fuel models generated by machines like the Mark I, long-range missions across the Pacific risked disaster. Pilots who never set foot near Harvard carried data created inside Aiken's laboratory on every mission. But the war wasn't waiting for machines to catch up. The pace of conflict accelerated, weapons evolved, and computational demands became even more complex. The Navy asked Aiken to begin planning successors: more powerful calculators, more efficient programming methods, and hybrid systems capable of solving problems beyond the Mark I's mechanical limits. Aiken responded immediately. To him, the Mark I had always been a first step, not a final answer. He began assembling design notes for a new generation of machines, the Mark II and Mark III, which would incorporate more electronics, greater memory, and faster logic. He didn't want his laboratory to remain a wartime curiosity. He wanted it to become the birthplace of a new discipline. But even as he prepared for the future, Aiken watched the world change in ways he hadn't predicted. Advances in science and engineering were reshaping warfare at a pace that blurred the line between invention and destruction. Radar networks covered coastlines. Proximity fuses redefined anti-aircraft strategy. The Manhattan Project crossed a threshold no one had crossed before. And in this new environment, machines weren't just tools. They were the architects of a new kind of conflict. The Mark I had made war more precise, but it had also revealed a truth Aiken couldn't ignore. As machines grew more capable, the role of human judgment became harder to measure. Engineers solved problems faster than leaders could interpret them. Data multiplied faster than analysts could think. Warfare began to rely on systems that few understood in full. The Mark I didn't win battles on its own, but it made possible a world where calculations moved faster than strategy, and where machines became trusted partners in decisions once made only by humans. It offered power and exposed vulnerability. Accuracy became addiction. Automation became expectation. When the war finally ended, the Mark I shut down for the first time in months. Its gears slowed, its relays silenced. Operators stood in a room suddenly quiet, aware that the machine had shaped the conflict without ever leaving its laboratory. But outside Harvard, almost no one understood what the machine had accomplished. Historians praised generals, pilots, and industrial leaders. The Mark I remained hidden in footnotes, overshadowed by weapons with visible consequences. And Aiken wondered, if a machine could influence a global war so quietly, what role would machines play in the decades to come, when they became faster, smarter, and more independent than anything he had ever imagined? When World War II ended, the Harvard Mark I had already completed tens of millions of operations. It had guided artillery, shaped naval strategy, refined torpedo models, and supported air missions across 2 oceans. But once the noise of war faded, its gears slowed to a calm rhythm. The machine that had served as a silent weapon was now facing a different battle, one that had nothing to do with strategy or conflict. It was the battle for the future. Howard Aiken understood that the end of the war did not mean the end of computation. If anything, the opposite was true. The complexity of peacetime, engineering, physics, aerospace, communication, research, required more numerical power than ever. Aiken saw a world where science would demand speed beyond what mechanical relays could deliver. The Mark I had proven a concept. Now the challenge was to build machines that no longer relied on moving parts, machines that replaced gears with electrons and relays with circuits. Even before the war ended, Aiken had begun working on the Mark II. It incorporated more electronics, faster switching, and an expanded ability to handle iterative processes. But electronics came with a new problem: reliability. Tubes burned out, circuits overheated, Signals drifted. The Mark I's biggest strength had been its mechanical stability. The Mark II demanded a different kind of engineering discipline. One Aiken approached with the same precision he demanded from his operators during wartime. By the late 1940s, the Mark III was operational, and the laboratory expanded again. Engineers, mathematicians, and programmers trained under Aiken's strict philosophy were now recognized as pioneers of a new field. Many of them, like Grace Hopper, would go on to shape modern computing. Hopper, in particular, helped transition the Mark II into a fully functional electronic system and later created the foundations of programming languages. Aiken didn't just build machines, he built people who would build the future. The machine line continued. The Mark III followed, a hybrid system with magnetic drums for memory and far more sophisticated logic pathways. It signalled that computing was no longer an experiment, but an industry. Aiken envisioned a future where machines handled complex modelling, weather prediction, communications, and even business tasks. While many engineers still saw computers as scientific curiosities, Aiken treated them like essential infrastructure, tools that would become as necessary as electricity. Despite his achievements, recognition came slowly. Aiken was not a public figure. He didn't seek fame, and he didn't craft narratives to elevate himself. He believed that machines spoke for themselves, through precision, not publicity. But history often rewards those who tell their stories, not those who build quietly. Aiken's work sat in the shadow of headlines about rockets, nuclear physics, and Cold War rivalries. Still, the impact of his ideas became impossible to ignore. The Mark I introduced the world to automated computation. The Mark II bridged mechanical and electronic systems. The Mark III embraced the future of digital logic. Every major computer built in the decades that followed, from mainframes to microprocessors, inherited concepts that had originated inside Aiken's laboratory: sequential programming, numerical automation, conditional operations, modular design. Even modern navigation systems trace part of their lineage to the computational approaches Aiken used during the war. As computing accelerated, Aiken watched the field evolve in ways that exceeded even his own imagination. Machines shrank in size but expanded in capability. Circuits that once required entire rooms eventually fit on small boards, then on chips, then on silicon wafers thinner than a thumbnail. Aiken had built a 5-ton machine to solve tables for the Navy. 30 years later, handheld devices could outcompute everything the Mark I had ever done. But Aiken never saw this evolution as a contradiction. To him, the Mark I was never supposed to be the pinnacle of technology. It was a gateway. A demonstration that machines could not only assist humans but surpass them in precision, consistency, and endurance. The war had simply accelerated the timeline. What should have taken decades happened in a few years because global conflict demanded it. In his later years, Aiken reflected often on the responsibilities that came with technological progress. He believed computation had immense potential for science, medicine, and communication. But he also understood something darker. Once machines enter warfare, they never leave it. The Mark I had helped win a war, but it also opened the door to a world where nations depended on machines to make life or death calculations. Accuracy could save lives or take them. Aiken rarely discussed this tension publicly, but his students remembered his warnings. He predicted that one day machines would operate faster than leaders could react, and conflicts would unfold at speeds no human mind could follow. He worried about a future where dependence on automation became irreversible. His concerns were not philosophical. They were based on lived experience. He had seen war lean heavily on computation, and he knew it would lean harder in the decades ahead. The Mark I was eventually retired, its massive frame preserved as an artifact of the early computer age. Visitors who see it today often compare it to industrial machinery, unable to believe it once performed calculations that modern devices complete in microseconds. But the machine's value doesn't lie in its speed. It lies in the fact that it proved what was possible. Aiken continued teaching and building systems until his retirement, shaping generations of engineers who carried his principles across the emerging world of digital technology. His legacy is not a single invention, but an entire philosophy. That precision is power, and that machines, when built with discipline, can elevate human capability in every field. But the moral question remains. In old right, one Aiken understood better than most. Did he help humanity progress, or did he help create a future where machines would control more than anyone ever intended?